In this part of the video, we are going to discuss about different configurations of tails. The design process of a tailplane can be generally split into 3 stages. First is to prioritize the different functional parameters of the plane, such as speed, weight, carriage ability, stability, aerodynamic efficiency, and etc. The importance of different parameters might vary based on different missions. For the DBF competition, there will be different missions every year, and a score will be given according to different parameters such as the speed, weight, and volume of the aircraft made. After knowing what function is important, we might approach to a conceptual design, which we choose a configuration that best fits our requirement. We might compare different conceptual designs using software such as XFLR. After having a conceptual idea of the aircraft, we could work on the detailed design with accurate geometry and dimension using engineering drawing software such as the SolidWorks. As I said, to begin a conceptual design, we would usually want to choose a configuration that is most suitable first. So, in the following time of the video, we are going to talk about the pros and cons of different tail configurations. We should know the pros and cons before adopting the tail, since they help us to decide which design to be used. In this video, I'm going to talk about the H-tail, T-tail, V-tail, twin vertical tail, boom-mounted tail, ringtail, and carnot. The first one to talk about is the H-tail. So let's begin with the advantages. First, the horizontal stabilizer will have a better efficiency compared with the conventional one due to the end plate effect. When the airflow across the wing, vortex and turbulence will be generated due to the separate flow in the wingtip. The vertical plate on the wingtip can prevent the vortex happening by blocking the airflow from the below to the top surface, which is similar to the principle of a winglet. This can reduce the drag and enhance the aerodynamic efficiency of the horizontal stabilizer. The second thing is, since the vertical plate is separated into 2, a shorter plate is sufficient. Having a shorter vertical stabilizer can allow a better later control. Also, when the aircraft is in high angle of attack, the influence of the turbulence flow from the main wing to the vertical stabilizer will be decreased. And since there are 2 rudders, the control surface may increase so that a better yawing control can be achieved, especially for low speed and taxiing. And lastly, for there is 2 vertical plates, even one is damaged, there is still another one that could provide the lateral control. For disadvantage, since there are 2 vertical planes instead of one which is in the conventional design, it might be heavier than the conventional design. For disadvantage, since there are 2 vertical planes in the H-tail where there is just one in the conventional design, the H-tail may be heavier than the conventional one. Also, in terms of the design, it is more complicated, and that may lead to a higher cost in manufacturing and maintenance. The second configuration that we are going to talk about is the T-tail. Similar to the H-tail, the T-tail also has the end plate effect to enhance the efficiency of the vertical stabilizer. Thus, a smaller vertical stabilizer can be used when compared to the conventional one. Second, since the horizontal stabilizer is placed on the top of the vertical step, it can clear from the turbulent flow generated by the main wing and the fuselage, and therefore improve the elevator performance and pitch control. However, when a wing is stalled at the high angles of attack, it may blank the airflow over the tailplane and elevators, and it may lead to loss in pitch control. Second, the vertical stabilizer must be made considerably stronger and stiffer, and therefore heavier to support the forces generated by the horizontal tailplane. Third, the control runs to the elevators are more complex, and the elevator surfaces are much more difficult to casually inspect from the ground, which lead to maintenance concern. The third configuration to be introduced is the V-tail. Since the vertical and horizontal stabilizer is merged together, the control surface was named rotavators, which is the combination of rudder and elevator. So let's talk about the advantage first. First, it is generally lighter compared to other tail configurations, and therefore it can have a faster flight speed. Second, there is less wetted area, so it will produce less induced and parasite drag. However, according to the study done by the NACA, it indicates that the V-tail surface must be larger than the simple projection into the vertical and horizontal planes in order to get a similar performance. So that, actually, the total wetted area is roughly constant. Third, the reduction of intersection surfaces from 3 to 2 produces a net reduction in the drag through the elimination of some interference drag. And lastly, the V-tail design is more resistant to spins and it is more effective at neutralizing them. The V-tail configuration, however, has experienced the history of fatal mid-air breakup during extreme stresses. Also, adapting V-tail will lead to a tendency for the aircraft to hurt around in yaw. And the rotavator will induce the undesirable phenomenon of the adverse roll-yaw coupling, which might also lead to a nonlinear control. And at last, to synchronize the rotavator to do pitching and yawing movement, the control system would be quite complicated. Then let's talk about some uncommon tail configurations: the twin vertical tail, boom-mounted tail, and the ringtail. The twin vertical tail is a tail quite similar to the H-tail, but the two vertical tails are no longer being placed at the end of the horizontal stabilizer, so there will be no end-place effect. It will also have a better rudder control since there are more control surfaces. Again, the shorter vertical stabilizer can lead to better lateral control. However, it will be more complex and heavier comparing to the conventional tail. For the boom-mounted tail, again it is very similar with the H-tail. The difference is the movement arm is a lot longer, and therefore it allows a better control ability along the pitch and yaw axle. For the ringtail is very stall resistant, so that it allows the aircraft to fly at a very high angle of attack. However, the ringtail usually needs to be quite large that the drag will be higher. Also, this kind of configuration is more complex and heavier when compared to other designs. For Carnot configurations, actually there are quite a number of them, such as the control Carnot, the lifting Carnot, tandem, free surface, and etc. In short, a Carnot configuration is putting the horizontal stabilizer in front of the main wing instead of putting after it. For general Carnot designs, one very apparent benefit of putting the horizontal stabilizer in front of the main wing is that it could be cleaned from turbulence flow generated by the main wing, and thus it can have a better control performance. Second, since the stabilizer placed near to the nose, it can act as the weight balance and make the nose naturally drop and prevent the aircraft from stall. For aft tail, it often produces negative lift, but Carnot often produce positive lift, so that using the Carnot configuration means the main wing loading is less. But there are still disadvantages for the Carnot configurations. Since the Carnot tail is close to the CG of the aircraft compared with the aft tail, the elevator needs to be deflected more to induce a larger moment. This may lead to a larger trim drag. Also, the distance between the aircraft neutral point and the aircraft CG is shorter for the Carnot configurations. And this makes the Carnot aircraft statically less stable in a longitudinal direction. Then, I'm going to talk about the two Carnot configurations, the tandem wing and the free surface. For a tandem wing, it can produce more lift. And as the Carnot tandem wing produces as much lift as the main wing, in this case, the aft wing would be influenced by the wake of the front wing, which is the tandem wing. And this may lead to weight penalty. The free surface configuration has both the Carnot and aft wing. They can act in opposite directions, thus cancel out each other's effects and allow the wing to operate with its optimal lift distribution. However, there will be weight and interference penalties, and the design is more complex compared to the other designs. That's all for our video. If you would like to know more, you can refer to this reference list, or you can find extra information at the libraries or from the internet. So thank you for watching, and see you in the next video. Bye!